Hello and welcome to online lecture number 16 for Chemistry 112 during the spring semester of 2020. In this lesson, we're continuing chapter 17. We're going to get into some applications of galvanic cells, also known as electrochemical cells. These are cells in which a spontaneous redox reaction occurs. So one very important application of these galvanic cells are the formation of batteries. Imagine what our life would be like without these portable sources of electrical energy. So we'll take a look at some details of several batteries that most of us are familiar with. First is the car battery, also known as the lead storage battery. This is a 12-volt battery. It's a 12-volt battery because there are 6 galvanic cells connected in series, where the positive post is connected to a negative post, positive post connected to negative post. As a result, then we can add up the potentials of each of these individual 6 cells to get the overall potential of the battery. So in any sort of electrochemical cell, we have both, of course, a redox reaction occurring, a cathode and an anode. Cathode's always where the reduction takes place. The anode's always where the oxidation takes place. So in the lead storage battery, both a form of lead is being reduced as well as a form of lead is being oxidized. So that our overall reaction looks like this to give us a standard cell potential of just under 2 volts. With our portable devices, often ran by AA, AAA, or single A batteries, these are known as dry cell batteries. They all give us the same potential of 1.5 volts, and they all consist of this overall reaction, where the zinc is being oxidized and the manganese is being reduced. It's a spontaneous reaction that's going to produce a transfer of electrons from the zinc to the manganese at a potential of 1.5 volts. Our next example are the NiCad batteries. These nickel-cadmium batteries give us a potential of 1.2 volts. That comes from this redox reaction, this spontaneous redox reaction where cadmium is oxidized, nickel is reduced. Notice that both products in this redox reaction are solids. As a result, these solids tend to remain adsorbed to their respective electrodes, which then allows us to recharge this battery. And when we recharge a battery, we want to get back to the original reactants in order for the spontaneous reaction to continue to occur, to produce electrical energy. In order to do that, we have to add an external source of electrical energy to force this reaction in reverse. So when we recharge it, we are going to be reducing the cadmium back to elemental cadmium and then reoxidizing the nickel back to its original form. This is a non-spontaneous process, which is why it takes an outside source of electrical energy to cause it to occur. But of course, recharging this process is not ever going to be 100% efficient, so there's always a limit to how many times we can recharge these batteries. So even rechargeable batteries, we can't use for a lifetime. Even rechargeable batteries, we have to replace every so often. We also have lithium batteries. These are very small lithium cell batteries, give us a very high potential of 3 volts. And what's nice about these lithium batteries is that not only does lithium have a high negative reduction potential, which means it's fairly easy to oxidize, it's also true that lithium is one of the lighter elements. So as a result, we get a lightweight battery, which also has fairly high voltage. So this is perfect for watches and other small devices where you don't want the mass of the battery to really contribute terribly much to the overall mass of the object you're trying to charge, trying to power. Then we have the lithium-ion batteries, most commonly found in our laptops or types of electrical cars. This is the overall redox reaction. And what's nice about this lithium-ion redox reaction is that because it involves lithium, it's going to be lightweight as well as really high voltage, and it's rechargeable, unlike what we saw with the lithium cell batteries. So batteries are typically desirable applications, good applications of electrochemical cells, but there are also other applications of these spontaneous reactions which we tend to try to minimize or prevent from happening. And these are typically involving corrosion. And corrosion is a general term describing the oxidative deterioration of any type of metal. So it's the reaction of oxygen with an elemental metal to oxidize that metal to another form. And we can see why those reactions are spontaneous, because we have the reaction of oxygen in acidic solution has a reduction potential of positive 1.23 volts, which means that any reaction of oxygen with any element below it on this table, less positive or more negative reduction potential, will be spontaneous. Primarily, we're going to look at the reaction of oxygen with iron, the so-called rusting reaction, but there's also the tarnishing of silver and the formation of patina on copper. And notice that both silver, copper, and iron, they're all three below oxygen on a reduction potential table. So all these reactions then will be spontaneous with oxygen. So with oxygen and iron, 1.23 volts, negative 0.45 volts. So if oxygen is your cathode, where reduction occurs, iron is your anode, where oxidation occurs, then the cell potential is going to be the difference between this number and this number. As a result, then, again, overall potential of the cell under standard conditions of positive 1.68 volts. Obviously, this reaction doesn't normally occur under standard conditions, but notice it's still positive, and so that's going to make it a spontaneous reaction. So in order for iron to rust, we need both oxygen as well as water. And kind of interesting about rusting of iron is that because it's a redox reaction, both oxidation and reduction occurs, and the oxidation, of course, always occurs at the anode, the reduction always occurs at the cathode, and the cathode and the anode are at different places on the iron. So at one point, the cathode is where oxygen is being reduced, and a different part nearby, but a different part of the iron is where the formation of rust will form, because that's where iron is being oxidized. So this is our overall reaction, and to form iron 2+, iron 2+ then will go on to be further oxidized into iron 3+, and then iron 3+ reacts with more water to produce this iron 3 oxide substance, which we associate with, we call rust, kind of a brownish red substance that is rust. And even though this is a solid substance, like the original elemental iron is solid, it doesn't have the same properties that the iron does. It's not as strong of a solid substance as iron. So as a result, this overall spontaneous redox reaction is weakening the substance, because it goes from a stronger elemental iron substance to a weaker iron rust substance. As well as rust tends to be more of a flaky substance, so when it forms, it's likely to fall off, which then exposes more of the iron to further oxidation. Unlike some of these other oxidation corrosion reactions, such as the tarnishing and the formation of patina, where they form actually oxidative, so protective layers, where only the top of the substance is oxidized, and that protects the rest of the substance from being further oxidized. But with iron, fortunately, that's not the case. So if we want to prevent rust, we want to minimize rusting or prevent it from occurring at all, because rust requires exposure both to oxygen and water, then to prevent rust, we need to keep the iron from oxygen and water. And one way to do that is to coat the surface with paint, most commonly grease or oil, and that will physically keep these reactive substances from having contact with the iron. It's a great solution, but unfortunately, it's only a temporary solution, because if you paint your iron fence, keep it from rusting, great, but then a couple years later, you're going to need to repaint that fence and keep it painted to keep it from rusting. A second method is to somehow electrically connect the iron to a second metal, a second more easily oxidized metal. These more easily oxidized metal we can recognize as one having a less positive or a more negative reduction potential. This is what's known as cathodic protection. So a very common application of cathodic protection is galvanizing. And galvanizing specifically refers to coating iron with zinc for cathodic protection. The idea being that if you coat iron with zinc, because zinc is more easily oxidized than iron, has a more negative reduction potential, when oxygen and water come in contact with the iron, the zinc is there to protect it. And any iron that already has been oxidized, this is a spontaneous reaction under standard conditions, where zinc will be oxidized and will be able to re-reduce the iron back to elemental iron. and so therefore maintain the integrity of whatever is being galvanized. So as a result, then the zinc would say it serves as a sacrificial anode because it's being oxidized in place of the iron that's being oxidized. We don't care so much if the zinc is oxidized, but we do care if the iron is oxidized. So with zinc being there, it's able to prevent the iron from being oxidized. Something has to be oxidized, so it's better that the zinc is rather than the iron. The most commonly seen with galvanized nails, typically a little bit more expensive, they kind of a grayish tone to them because of the coating of zinc, but especially useful, especially important with any applications that are exposed to the elements, any outside applications. Another application of cathodic protection is when we protect iron structures that are buried deep underground, where it's not practical, certainly not cheap, to constantly replacing the iron pipes that we have buried underground. So one way to prevent that iron from rusting, because it will still be exposed to oxygen and water, is to connect it to some sort of sacrificial anode, and magnesium is a very common example of a sacrificial anode. So as a result, when corrosion occurs, it's going to occur at the sacrificial anode rather than the iron pipe. And it's much easier and much cheaper and much more practical to periodically replace the sacrificial anode than it is to replace the iron pipe. So what we want to be able to do is determine which metals will or will not work as sacrificial anodes to prevent the corrosion of a different metal. So based on what we talked about in the last slide, we have magnesium, zinc, copper, and aluminum. We want to try and prevent specifically the corrosion of iron, given their electrode potentials. These are, of course, the reduction potentials of their respective half reactions. So you see, of our choices, copper is the only metal which has a electrode potential that is greater, more positive than that of iron. So copper would not work as a sacrificial anode. The actual reaction where we can imagine it working actually has a negative standard cell potential. So this process is non-spontaneous. This is showing copper being oxidized instead of iron being oxidized. At the reverse, where copper is being reduced and iron is being oxidized, then has a positive cell potential, which means that copper would not actually prevent iron from being oxidized. Copper would actually promote the oxidation of iron. So for iron, we could use zinc, aluminum, magnesium, or any other metal whose electrode potential is less positive or more negative than that of the metal we're trying to protect. Copper wouldn't work, and silver would not work as well.